Right, welcome to lecture 21, which would have been on April 6, 2020. So here we go. We would have been playing Electron Blue from REM, the album Around the Sun, coming in, so if you are so inclined, cue that up to get the real experience. Today we're talking about what's covered in intro sections roughly 8.6 to 8.9. And so in relating this to some of the course learning objectives, we're going to understand the concept of effective nuclear charge and how it affects atomic size, ionization energies, electron affinities, and metallic character. So by the time we're done today, I think we get 5 videos, but they're all pretty short. You're going to be able to identify the trends in atomic size, ionization energy, electron affinities, and metallic character. And you're going to be able to explain these trends in terms of electron configurations, which is kind of the whole point. And at the end, you will know which one will blow up more when you put it in water, lithium, sodium, or potassium. All of these trends, atomic radius, ionization energy, electron affinity, and all that stuff, can be explained by this thing called shielding. And shielding is the notion that not all electrons feel the same attraction to the nucleus. So what I've got here, stolen shamelessly from your text, is a figure of stylization of a random lithium atom. Lithium is element number 3. It has a +3 nucleus because it's 3 protons. Now, electron configurations. Lithium has 3 electrons. 2 of them are 1s electrons, so that would be this one here, this one here. Now we know that electrons are wavy, they are not point particles, which is what this whole kind of shady blue area is. So this represents the cloud that those 2 1s electrons would occupy. And note they are a certain distance from the nucleus. The third electron in a lithium atom is a 2s electron. And because it's a 2s electron, it is further out than a 1s electron. So it's out here beyond the whole blue fuzzy area that defines the 1s electrons. Now, I think I've thrown this word out before, but we'll say it again. So the outermost electrons grouped together are called valence electrons, and the ones inside are called the core electrons. Since these electrons are closer to the nucleus than that 2s electron is, they sort of shield the electron, or shield this electron from seeing the full-on +3 charge of the nucleus. And this is the idea of the shielding. And in the most simplistic case, each electron that is closer in can negate 1 proton from the nucleus relative to what the outer ones are going to feel. And the result of this approximation is called the effective nuclear charge. And so the idea is that, and it's equal to, the actual nuclear charge is +3, because it's got 3 protons. And from the standpoint of the outermost electron, that single 2s electron, it actually only feels a +1 charge because these 2 electrons essentially cancel out 2 of the protons. And so, and this concept, this result we refer to as the effective nuclear charge. Now, remember that the effective nuclear charge is different for each type of electron in there. So for these 1s electrons, there's no electrons closer in, so their effective nuclear charge, what they feel, is basically +3, the same as the actual nuclear charge. So this is the simple idea that this outermost electron doesn't feel the full nuclear charge because the other electrons are between it and the nucleus. So let's build on this a bit. All right, so here is a, this here is a representation of a sodium atom. So let's talk about the effective shielding here. So electrons in any given shell are going to be mostly shielded by all the electrons in any shell below it. And when you've got a filled inner shell, one that's completely filled, those shield much more effectively than electrons in the same subshell will shield each other. And obviously electrons, any one electron is not going to be shielded by any electron in a shell above it. So that would be an electron that is further out. So now, for example, let's look at sodium, and let's actually look at two different types of electrons. So this neutral sodium atom has 6 2p type electrons. Any one of those 6 individually is shielded by the 1s electrons, the 2s electrons, kinda, and a little bit by its neighbors in the 2p subshell. But that's not really particularly interesting because it's the furthest electrons out, those valence electrons, that are interesting because they're the ones that do the chemistry. So let's consider the shielding situation of that lone 3s electron. And it's shielded by the 1s electrons, the 2s electrons, and all of the 2p electrons, so a total of 10. Now let's go 1 over to magnesium. This is element 12. So it has 2 3s electrons, but it's going to be the same idea. So let's consider how strongly attracted those outermost electrons are. You know, these 3s electrons, both of them. And so the rule that we're going to come up with here, let me bring up the figure. Let me go here. So the effective nuclear charge basically says that is equal to the actual nuclear charge, which is what that Z is, minus the number of shielding electrons. Now, being able to figure that out is kind of key. And what our rule here is going to be is that the shielding electrons are all of the electrons in any of the shells below the electrons that you're talking about, and that's almost always the valence electrons. So these electrons here are 3s type electrons. So any electrons for which n equals 2 or n equals 1 are going to be shielding electrons. And there are 10 of them. There's the 2 1s, there's 2 2s's, and finally 6 2p's. So plugging into our handy dandy formula here, the effective nuclear charge is going to be the full nuclear charge, in this case 12, minus 10. So each of these valence electrons, the 2 3s type electrons, actually only feel a +2 charge from that nucleus and not the full-on +12. So now that you have a sense for how we determine or how we calculate the effective nuclear charge, bust out your periodic table and let's answer a couple questions. So what I want you to do is take a minute to understand or try to figure out how the number of shielding electrons changes going across from left to right in any one particular row of the periodic table. Hit pause if you need to think about it. And the answer is it doesn't. So remember, all of the screening electrons are all of the electrons in the shells under. In any one row in the periodic table, you are filling in any one particular shell. So the number of screening electrons actually remains constant until you start a new row, in which case the number jumps up quite a bit. So the next question is, how does the effective nuclear charge change going left to right across the row? And the answer to that first question is part of this, so think about it for a sec. And the answer is it continually goes up. So what's happening? Well, we've got the same effect, we've got the same number of screening electrons, but we are subtracting that constant number from an increasing actual nuclear charge. So the effective nuclear charge goes up by 1 unit each time you go for each element. All right, so these two trends are actually very important. And so these are ones that you need to know. Shielding electrons remain constant in a row, and the effective nuclear charge actually increases as you go across a row from left to right. Now, one more. Let's consider the other direction. We're going to go down a group. So again, think about how that number of shielding electrons is going to change. And it goes up by quite a bit. So each time you are adding an entire shell's worth of shielding electrons. And the next question that follows is, how does that effective nuclear charge change going from down a group, let's say top to bottom? And hopefully you came to the conclusion that that actually remains constant. So the idea is that yes, each time you go from one group to another, you are adding an entire you are adding an entire new shell of shielding electrons, but you're also adding an equal number of protons. So in the end, the difference remains constant. So everything in the same group has the same effective nuclear charge. Also an important thing to take into account. So these two notions, how the effective nuclear charge changes going from left to right across a group and top to bottom down, is the basis for how these trends, how these properties we're going to talk about, like atomic size, change in that same way. And we will start that at the next video.